Okay, so in this example, what I'm going to cover is a multi-group confirmatory factor analysis. And the way that I'm going to do this is use the Brown steps from his Applied Confirmatory Factor Analysis book. And there's also different terminology within this field, and what I tell you to do is pick the ones that your field tends to use the most. So I'm going to go with the ones that we in psych tend to use the most, and so that's where the naming is going to come from. And what I'm going to do is look at a particular scale. I'm going to use the resiliency scale 14 because I have some data from a project on that, and see if that scale is invariant. So invariant means that it's equivalent across groups, and we're going to use ethnicities, so we're going to do black and white, and see if there's a difference in different parts of the scale between these two groups. And so a multi-group analysis really can have two purposes. You can, if you're doing more of a confirmatory factor analysis, look to see if the scales are totally invariant, which means that they're equivalent. And that would be good, because that means no matter who you give the scale to, or different ways that you're giving the scale, or different time periods, that implies that the scale does the same thing every single time. So we're assessing the latent variable in the same way, no matter who is taking the scale. So that would be a good thing. Another reason you might be interested in doing these is to see where these systematic differences lie. So in a scale development kind of area, you might want to get rid of questions that aren't invariant because you want them to be the same. Or it's at least interesting to know where these invariant, non-invariant pieces lie, because that might be driving differences you see. So for example, let's say we had two questions on this scale that turned out to be non-invariant, so they're different between our two groups, and that might be the reason why you get overall total score differences or average score differences between these groups. So it looks like, you know, they have different resiliencies, but it's actually being driven completely by one or two questions. And so is that a difference in resiliency, or is it a difference in the way these particular questions are worded? And you see that with people working on like IQ tests to try to make them culture free, is what it's called sometimes, because you want to test people's latent trait. You don't want to test other variables and interact with those traits. And so trying to understand where these small differences may lie that then drive the larger scale differences can be really important. Okay, so that's kind of a brief overview of why you might use a multi-group analysis. So let's try one. Okay, so we're going to use this resiliency data set and then test a couple of different things. So let me scroll down here. So I've got my little chart. This isn't all the fit indices you may want to include. I'm just, for the example, I'm going to include these. And the first thing you want to do is test to make sure that everybody all mixed together is at least a good fit. So with factor analysis, you've probably already done an exploratory analysis, or someone has. So you know that the questions should at least load onto their factors. And if they don't load onto their factors, you may have a bigger problem. One more about factor structure rather than multi-group differences. And if you think about it, in an exploratory analysis, if a question is a positive for one group and negative for another group, it's going to wash out, because when you look at loadings in an EFA, the loading will average out to something very small, like close to zero, if there are big group differences. So EFA kind of protects us a little bit from having big group differences, because if there are big group differences, that will sort of make the question get eliminated, because it'll create this sort of average score that's a zero for it. However, if there are differences where they're both the question is good for both parties, but one party is even stronger, as long as both of them are strong, we won't see that that's a difference. We'll just see that it's like a strong question. So this really will help you get at one group has a much stronger loading or a much higher intercept, whereas if they have different signs, where one's positive and one's negative, that probably won't make it through the scale development process, but it may happen. So we're going to test all groups to make sure that the CFA fits at least well, because then a multi-group analysis would be appropriate. And then we're going to test each group separately. So we'll test just whites by themselves and just blacks by themselves, because then that we'll be able to make sure that they at least, the models will run. And then we'll start to nest them together. So with the first 3 models, really the first 4 models, you're just sort of looking at the fit indices to make sure they're okay. And with this, as we go, the fit indices will get worse. So the first model needs to really, all groups together, have a good fit. And then after that, because we're subsetting groups and because we're adding constraints, the fit indices are gonna get poorer usually. And so that's okay. And then we're going to walk through the 4 steps of invariance testing that are probably the most common. There are also some other steps that you can do that I'll talk about here in a minute, but we'll walk through all 4 of those. And I'll talk about what they are as we go. And then just a couple little questions of like, how do I know what's going on? So let's start by programming an all groups model and just go over basic CFA procedures again. So the first thing you always want to do is load the library. I've probably said that 600 times in every video, but it's true because if you don't remember to load the library, it most certainly will not run. So I'm going to use lavaan to do my structural equation modeling and semPlot to make a picture of at least the first model so that I know that I'm doing everything right. I'm going to load my data now. So I'm going to import the data set. So I'm going to use the import data set over here from text file. And then let's find this data. So multigroup data here. So it should have the resiliency scale. Great. I'm going to call it something great like data. And I'm going to include that header so that R will interpret those as variable names and not just a row of data. So click import. Okay, so it shows me the data. Looks pretty good. And I'm going to copy this line down here so I don't have to remember where the data set is. I want to do this later. Now, generally, you're also going to do data screening. And so you'll already know the answer to this question, but since I'm not showing you data screening in this example, and if you're interested in data screening, I have another video on how to do that in R. What I'm going to do instead is sort of do a quick screen of the variable. Okay, and that's mostly because I haven't done data screening. So we're interested in the race test variable. So I'm going to pull that variable out and look at it. Okay. So currently at the moment, I could also look at it here. It's an integer because I have it labeled 0, 1, 2, 3, or 0, 1, 2. And so it's not a factor variable, which is okay, but it would be better if it were a factor variable because that's what it is. And I have 52 people in a 0 group, 100 people in the 1 group, and a bunch of people in the 2 group. Well, I've told you over here that the 1 group is black and the 2 group is white. So that's the only thing I want to use. So I want to exclude all those other variables, all those other groups first, otherwise it will test them all together. So since we're only going to do this analysis on blacks and whites, I don't know that it's fair to add the extra 52 people in to an all groups analysis because they're certainly going to get excluded here in a minute. So let's exclude those people. So I'm going to make a new data set where I'm going to subset the data. So there's a bunch of ways to do subset, but I really like the subset function. So I'm going to subset data where race test is greater than 0. Okay. I also could do race test equals 1 and race test equals 2, but since this is an integer still, I want to do it as greater than 0. Okay. So that should leave us with like 460 something. Okay. So now if I did this table, ran this table again, I'd see I only have 1s and 2s. Very cool. But let's make this a factor. So the only reason I'd suggest doing this if you have 1s and 2s is so that when you look at the output for the multigroup analysis, you know which group it is. Because honestly, 6 months from now, when you are trying to fix something that a reviewer has suggested for you, you're not going to remember who 1 and 2 is unless you have great notes somewhere, so you might as well put it in where your analysis is. So let's fix that variable. So I'm going to fix just the race test variable and do a factor code on it. So the factor thing will change it, factor function, not thing, will change it over to a factor variable for us. And so if I can remember all the commands here, I want to do data race test. I can't remember the commands off the top of my head, so let's look them up. Okay. So the first thing you do is the variable name, and then the levels, and then labels. So I know I gotta have at least the variable name in here, and I think I can just do labels. Now the labels have to be in the same order as your variable, so let's do black for 1 and white for 2. Let's see if that worked. So I'm going to rerun that table one more time. Okay, and now you'll see that it's factor with 2 levels over here, so the type is a factor, and it gave me black and white as the labels. And so all I really needed was the variable I want to change over and the labels for them. You can also do what the levels are supposed to be. Alright, so that just gives me some quick screening, and that's something I would actually do in data screening, but since this example doesn't have data screening, just to show you how you can do it. So let's do all groups first. And so I've got to program a model. So my overall model is going to be that resiliency is equal to, it's approximately equal to, right, all the questions added together. This is a one-factor model. So RS1 plus RS2 plus RS3, etc. So I'm going to make this go a little faster. So there are 14 questions. Don't add 13 twice. Okay, so I've just got all the questions added together for this particular model. And I can check and make sure that looks okay here in a minute by creating a picture of the model. So this I shouldn't label as all groups. I should just label this as the model. The model isn't going to change throughout this analysis. We're going to change the way the model is constructed. So the first thing we're going to do is all groups together, ignoring the distinction between black and white. So let's call this all groups that fit. Let's use our CFA function to run a confirmatory factor analysis, because that's what this is, on our model. And we want to tell it who the data is. The data equals data that I've currently stored. And then on these particular models, I don't think we need anything else. Oh, lies. You do need one more thing. It's called mean structure. Okay. And so we're going to turn mean structure as true, or turn it on. Oops. True. Okay. And what does that do? Well, that adds intercepts and means to the model. So the intercepts will be on the manifest variables, or the squares, and that you can think of that as the y-intercept for each manifest variable, which honestly ends up being the average score for each question. And so we're going to estimate more things in these types of models and include the average score for each question, which is the intercept. And it also creates a latent mean, so the mean for the latent variables in the model. And these are called means and covariances models, because covariance models are what you normally do. We're adding means and intercepts. Intercepts are really means, but they're means for the question, so it's like the intercept for each question. It's not like it. It is the intercept for each question, and so we have more things to estimate, so our degrees of freedom are going to be different in these types of models. And why would we do that? Well, when you get into testing the invariance steps, you'll test whether or not intercepts are different. And so you wouldn't want to do an all-over CFA test without those intercepts, because then you'd be comparing models, or you don't compare them directly, but you kind of look at them. You'd show that like these models run, but then you'd add means and intercepts later, and so they're not totally comparable. So you want to make sure that you use means and intercepts in these types of models when you're going to do a multi-group analysis. When you're not going to do a multi-group analysis, it's actually traditional to leave off means and intercepts. So let's run that. Object model not found. Oh, oops, I forgot to run this. There we go. So it ran fine. So let's look at a summary of that. So let's turn on standardized equals true, and r square equals true. So we can make sure we don't have any Haywood cases. So I'm looking at this. I've got my latent loadings, which aren't too surprising. If I look at standardized all, they're all very strong, so I know that all the questions load appropriately on their factor. If I look at intercepts, in the unstandardized column, that is the average for each question. So on that one, I'd probably want to look at it in the scale of the variable, so I'd use the first column. And those aren't too surprising because this question is, I think, a 1 to 7 scale. It might be a 1 to 9. I can't remember off the top of my head. And those loadings are not too unusual in a scale where 4 is neutral. Okay, so it's probably 1 to 7. I got the variances for each question, which look pretty good. And then none of my R-squares are over 1. So my variances are positive, my R-squares are below 1, so I don't have any Haywood cases. Let's pull out the fit measures for this, though, and look at how those line up. So is the model any good? I know I have good loadings, but is the fit any good? So I'm going to cut and paste. So it's 77 degrees of freedom for this chi-square, or for this model. And I'm going to cut and paste this value here, chi-square. So that's clearly going to be significant, but most of the time chi-square is significant, so it's not a huge deal. Okay, I have 0.925 for my CFI. That's in the acceptable range. My RIMC is 0.086. It's also acceptable. It's not great, but it's acceptable. My SRMR is 0.041, and that one's in the excellent range. Alright, so there's SRMR right here. So overall, this model's pretty good. Okay, and these NAs really out here should be on all 4 columns. Okay. So I would say this is a pretty good model, and I would keep going. And so a model with all groups included is fairly good, and so our resiliency model seems to be appropriate because it has good fit indices and good loadings. So then we would move on to the next step, which is to split into groups and test each group separately to make sure that you get the same basic fit indices for groups separately. So the next thing we want to do in this example is to separate those groups out and test the model individually for each group. Okay. So as you remember, we have groups that are black and white. So I have that stored in a variable called race test. So I have about 100 in the black category and 350 in the white category. In a perfect world, these would be more equal, but it's often hard in our neck of the woods to find different ethnic groups. So this is what we got. And let's program some separate group models. And so what that will let me do is test and make sure that these are going to run for each group separately. And that's important in the sense that if they don't have the same picture in the model, if you think about the structure of the model, and we can create that picture with our sim paths. So the code is sim paths, the model name, so that's all groups.fit. I'm going to give it some labels. So what labels? And let's give it the standardized labels. And then if you give it the layout, I think tree is automatic, but tree is a good one for a CFA model. And so we have this picture of the resiliency scale where everything loads onto one giant factor, and we can see here that we have the mean structure, because we've got this little triangle out here. So we're estimating means and intercepts, and this is sometimes called a max model, means and covariances. And so I want to test to make sure that each group separately runs. Because if one group doesn't run, that's a good indicator that a multi-group model would break down, and you should see what it is about that group and talk about a little more global differences. Now, in a sense, when you program everyone together in one giant model, ignoring groups, often the fit might be bad because maybe one group didn't run or has totally different loadings, or the paths are going in different directions. And so often we will, you won't see any issues in this step because of the way we do scale development. So if a question is good for one group and poor for another group, or if a question is positive for one group and negative for another group, often in an EFA, those will cancel each other out, and so the loading will be close to 0, so you would have nixed it already anyway. But it is important to stop and to look at each group separately, because that will indicate whether or not the next steps of actual programming of a multi-group model are appropriate. So let's create ourselves separate data sets to do this. So let's make a white data set. So I'm going to subset. So the subset function can be used to subset data. You could also do the normal subsetting rules in R. I just happen to like the subset function because it's clear what it's doing. So I want to subset out my data, and I want to use the variable race test. So it's data where the data set is, and then the variable rule. So I want race test, and I want it to be equal to white. Okay. You do have to spell it exactly the same, which is why we're in my little table down here. It does have to match, or it will pull nobody. And remember, this is a logical operator, so it's not 1 equals, it's 2. So I want everything where everything is equal to white. Now I could select particular columns. So you could do a thing here and say select columns 1 through 5. I'm just going to leave all the columns in there, so I don't need that next line. So if I've done this right, the data set that loads should be 358 people. And that looks like what happened. So my white data set has 358, which is what I was expecting given this table here. Okay, so always check, because if your subset doesn't work, you may run your next models on the entire data set again. Okay? So let's make a black data set. And should have 100 people. Great. Okay, so we have our 2 data sets separated out. And then I essentially want to do this exact same code that I did for all groups. So I'm actually just going to copy it to save a little bit of time. And I want to do that same thing twice, once for each group. So I'm going to do this as the white group. Now I have my model. It's the same model. We're using the same model the entire time. But now I want to change the data to be my white data. And then for my summary, I want to just change all of these to be the same name. Then we're going to do the same thing down here. Change this data set to black. And black dot. Okay, so we're trying to see if both groups have the same fit for this resiliency scale, and it's the same, approximately the same structure. So this, if there are problems here, this will really tell you that the structure of the scale is different for each group. So let's run that. So we got our summary here, and again we'd want to look at just the different numbers. So all of them appear to load in this standardized column fairly strongly. The intercepts are 4s and 5s, so it's not that different from our first model because the white group makes up such a large portion of them. All my variances are positive, and all of my R-squareds are less than 1. So that was doing pretty good. Let's get the fit indices for this group. I'm going to show you kind of a trick to make this go a little faster if you know which fit indices you want. So I haven't really showed this so far, but it would be fit.measures. And then I want to concatenate, I want to do a group of them. So if I did them in the order I wanted, I would do degrees of freedom, and then chi-square. And that's because I always use these particular ones. So let's look at our Word document here that we've been using. And talk about only looking at the ones we're interested in. So we have chi-square, degrees of freedom, we want the RIMC and the SRMR. SRMR, and then CFI, I believe. So you can continue to look at all of them, or you can parse it out and tell it, I only want a couple of them, I don't need to see all this stuff. And what that'll do, and you can put them in any order you want, is set it up where you don't have to type that 1,000 times, or you don't have to copy and paste all of this stuff and then search for the ones you want. So here's our set. This is really good if you're making lots of tables for this sorts of thing. There's one other trick you can do here that would make this go even faster. Is I'm going to take that out of my data here and stick it here and just call it order. So I've called that order. Now I'm going to paste that variable down where I have fit measures, and that should give us the same thing. So this is the order of the fit measures that I want. You can call it whatever you want. Here are the fit measures I want. And that will allow me to do this kind of quickly and not have to search for the ones I'm looking for. So kind of a quick tip late into the semester on how to only pull out the ones you're interested in. Alright, so the next thing here we want to do is look at the fit for this group. So the chi-square is 342. And it's not that different from this chi-square. Now it's the same model, so you'll have the same degrees of freedom. RMC is 098. RMR is 047. CFI is 902. Now, almost always, once you start building these models, the fit will drop. And you have to think about when your all groups model, you have a lot of people. So you have 500-600 people, and then when you split those in half, you're losing people. And when you have smaller samples, the fit can still be good, but it tends to be worse than larger samples just because the more information you have, the easier it is to estimate, unless it's a really crazy model. I mean, this is all things given. You know, the fact that the model is actually okay, that sort of thing. Because if you have a bad model and then you subset out groups, you might still have a bad model. But the fit will almost go down. So at this step, it's really just making sure that it isn't too crazy different. Most people do not do comparisons here because with the rules that we're going to use, this would be a significant difference. But the white group makes up, 3/4 of that data. And so it's really just a sample size drop. So we just want to make sure that it isn't too bad. Okay, and these are all within the acceptable range. The RMC is less than 0.10, SRMR is great, CFI is in the acceptable range, so we're doing okay. Alright, so let's try a black model here. So look at my summary, all my R-squareds are good, my variances are positive, my intercepts are looking pretty good, and then all the loadings appear to be large and they all load onto their one factor. So that part's good so far. Let's look at the fit indices. And this model's actually better. So what you'll see is that the overall model is usually kind of a weighted average of the original models. So if you look at the fact that this is 0.86 here, remember that white makes up more of the data set, and so it's a weighted average toward of our fit indices here. So this model's pretty good. Oops. I mean, that's not a perfect comparison, this weighted average. It's the idea of it because, I mean, look at RMR here. And so for both groups, our models seem to fit appropriately. And so that to me implies that we could move on and try the multi-group steps because the model appears to be the same. Now the way to test that is actually configural invariance. So configural invariance, what we're going to do is take those two models where we had them separated out into two totally separate models. So it's kind of like keeping people in different rooms. That's actually probably a terrible example since I'm using ethnic groups here as my example, but if we were to keep everybody separate, now what we're going to do is merge everybody into one group. So it's called nesting the models. I always think about this as pancakes because I love food examples. And so what we're going to do is, in my class we joked about the pancakes were on different plates before. Now we're going to put all the pancakes on the same plate and stack them together. And so what that will tell me is if the two groups share the same structure when forced to have the exact same structure. So before, when we tested them separately, we could have changed the structure. But in this particular example, now we're going to nest them together and test if they have the same structure. So are these pancakes the same size, essentially? And so to do that, we're going to use the group function that's part of the CFA code. And then from here on out, we're going to start testing the models against each other. So what we're going to do is let's do configural invariance here. So now I'm going to nest everybody together. And so I'll just type this one out. It's a CFA, right? And we're still testing that overall model. So I'm going to use my model. Here. I got my data. I'm going to go back to the original data set because I want to use everybody together. If you try to use the two separated data sets, it will have a fit. Our mean structure is still true. Now, that's automatic when you start doing these group functions and testing against each other, but I think leaving it in really helps you understand why you did it before. So keeping that mean structure, using it throughout will help you see that this is a means and covariances model. Even though that code isn't quite required right here at this point, I think if you know that you've got to do it, just continuing to do it helps you keep you straight, basically. All right, so the next thing we want to do is program in a group variable. So you're going to use the group code, and it's a variable column name, so it needs to be in quotes. We're going to use race test. Good gracious. And that's why at the beginning of this analysis, I really made sure that I eliminated things I didn't want to use. So we went through and excluded the other groups because it will program as many groups as there are in that variable. It also helps if you add the labels like we did at the beginning because then your output is labeled appropriately. All right, and that looks like it's going to be it. So we're really only adding from this overall model here at the beginning this group function. Okay, we're going to do some other things here in a minute, but that's the only thing we're adding. Okay, so then we'll want to take a summary of that configural fit. Okay, and I always use standardized equals true and r squared equals true. So let's run that first one. So it ran. Get our summary. Now here's what's happening when you look at the summary here. So let me go to the top. You will get one overall chi-square. So we're going to look at the fit indices here in a second. But you're going to get a chi-square for them nested together. So this is one model. It's not two. But it does give you the chi-square for each group. So you could make sure you did it right. So I got 125, 342. Now 125 and 342. The problem is that it does not actually give you all the fit indices if they were totally separate. So don't let this confuse you. That is from the previous step you just did. It will give you that, but it won't give you everything. So you can't skip the step we just did. Okay, darn. So it gives me group 1 appears like it's our black group because they're coded higher because they're higher in the alphabet. And right now, all the variables are allowed to do whatever they want. So in a multigroup model, we're going to constrain parameters slowly until it breaks. So we're just adding more and more restrictions until the models go, no, can't do this, and we're not the same anymore. Okay. And so what we're doing here is we can look at each group separately. So these should be roughly similar to the ones we just saw. And then it'll give me my white group separately. Scroll, scroll, scroll. And then it'll give me my r squareds. Okay. And that's pretty much the same thing we've seen before, so I'm not going to spend a whole lot of time looking at it. Let's look at the fit measures. And you'll notice that it gives us one set of fit indices. Yes, there are two groups here, but it is still one model. These two groups are forced to be the same, in the same, two pancakes on the same plate. And so it's one fit for the model. You'll notice that the degrees of freedom have doubled. Basically, the whole model's kind of doubled in size because now we're estimating both groups. And so each little square gets to count twice, so you get a lot more degrees of freedom. And the degrees of freedom will increase as we go because as we constrain things to be equal, we're estimating less numbers. Oops. So 468, 758. So the chi-square is probably significant, but again, we don't really put a whole lot of weight in that. Our RMC is good. Our SRMR Our RMC is okay, our SRMR is good, our CFI is acceptable. So when these two pancakes are forced to be on the same plate, they appear to both be pancakes. Okay, so we don't have like pancakes and a waffle, right? So what we're going to do now, so that's configural invariance. Configural invariance, remember, is they have the same picture or the same configuration is the best way to think about it. Now what we're going to do is metric invariance. And metric invariance allows us to look at the loadings. So let me go back to R here. We get the loadings of each item onto its latent variable here. And now what we're going to do is force the loadings for each group to be the same. So are the weights essentially from the latent variable to the manifest variables is the same for each group. Now to do that, I'm basically going to take this configural invariance code. This is going to be metric invariance. Remember, these are the terminology from the Brown book. Other people use slightly different terms. And so what I'm going to do is I still have my data set, my mean structure, my group. I'm going to add one more piece. And what we're going to do is group.equal. Okay, so set these two things equal across groups. And I'm going to set the loadings equal. So you type it just like that, loadings. Now I've included the little concatenate function because in a minute we're going to copy this and add another one. So you didn't need it at first, but you'll need it for the next step, so go ahead and stick it in there. And then the rest of this all stays the same. I'm just going to change the name so I can have them saved in different places in case I want to look at it again here in a minute. So let's try forcing the loadings to be the same. So now we're checking to make sure they're both chocolate chip pancakes. Right? And what you'll see as you look at this is something new happened. So here, this right here is where I got some code that has an extra piece that I haven't seen before. And what that is it sets, that's what it's telling you, is it set this particular loading to be P2. And if it's as I scroll, I'm going to go down here and look at my second group. This one's also P2. So this is just the code marking, denoting like what other one it's equal to. So this is where they line up and they match. And you'll see that the loadings are now the same. So 1.24, 107, 1.24, 107. So we forced those to be the same, and now we have little markers that indicate how they're matched across groups. Let's look at the fit indices. So this should be the fit for loadings and structure is the same. So you'll notice our degrees of freedom have gone up because we have set things to be equal. And so when you do that, you get some of the things you were estimating before back. So fit's still okay. And our CFI actually hasn't changed at all. And so that usually will happen when your models have almost exactly the same fit. So it's not quite going to always be perfectly the same. It just happens to be in this particular example. And you'll see that when the loadings are very, very similar, or whatever you're testing is very similar. So how can I tell if adding this restriction worked out okay? And what you do is you can do a nested chi-square test, but those are heavily biased by sample size, and so people are moving away from them. So you could subtract and say it's 167 minus 154, and then 483 minus 468, basically subtracting this column, and tend to go with, I'm going to butcher these poor people's names, it's Chung and Rinsvold rules. They've written several papers on this exact issue, on partial invariance and how do I compare invariance models. And so one of the rules that they use is a change in CFI. So the change in CFI needs to be less than 0.01 for the models to be the same. If it's greater than 0.01, the models are different. Okay, they've also suggested a change in McDonald's non-centrality parameter, which you can actually get out of using lavaan and R, which is really awesome because it's not easy to get out of some of the other programs. And they have a couple of more examples, but the one that's really taken speed that a lot of people use is this change in CFI rule. And so what I'm going to do is I'm going to say that change is 0, 0, 0. I'm going to use 3 decimals because it's a 2 decimal rule. And I'm going to say that no, there's no difference between the metric model and the configural model. So that means that the loadings are the same. Okay, so this one's all about the picture. This one's all about the loadings. So those loadings across groups are roughly equal, which is great because in a sense that means that I can use this scale for either group and I know that each question has the same weight to the latent variable across groups. So that's kind of cool because it means that the questions all are linked the same to the latent variable. Now they're all not equally weighted because some questions are better than others, but they're equally good for each group. All right, the next piece we're going to try is scalar invariance. And the great thing about coding this in lavaan is it's really easy to just keep adding in the next step. So I want to do scalar invariance. So I'm going to change my, copy and paste my code from above and then change it up. So I want to do my scalar fit here. Alright, so stale data is data, mean structure is still my same group. But now what we're going to do is in this group.equal, we're going to add intercepts. So scalar invariance is about the intercepts, which we were talking about being basically the average score for each question. So I know how much each question is weighted towards the latent variable, and what you do is you take those weights and you multiply them times the actual question, like the actual answer that a person wrote for a question to get your latent means. But where do people start? So a way I think about this is this sort of average score for this question, or if you think about these being sort of positively related to their latent variable, this is sort of where the question on average starts. So most people are picking 4, and then it really can only go up from there. But remember, it's a y-intercept, so it's an average for the question. And sort of how much extra do you get by adding more points? So if a person marks a 4 on this, it'll be multiplied times their loading weight. But in general, the average for this question is a 4.5, that sort of thing. All right, so let's try writing that. So something new now, all the intercepts will have more numbers, so we're forcing all the intercepts to be the same across groups. And I've published several of these examining different scales, including this one actually, and I would say generally, from my experience, obviously this will be different for other people, this is where it breaks. So if a model is going to have trouble, it's often in the intercepts, and that is because while people may have the same weight for each question, they may not start in the same place. So white participants might tend to mark this question as a 5, whereas black participants tend to mark this question as a 3, but the weight of the question is the same. So the slopes are the same. And so it's kind of like in an ANOVA, you would say they have different means, but there's no interaction between the means and the slopes. And so often this is where it's going to break down, if it's going to break down at all. And we'll see what happened in our particular model. And so we can look at those loadings, but instead I just want to look at the fit indices. So let's see what happened. Let's go back to Word. So I've got 180 degrees of freedom. RIMC didn't really change a whole lot. My SRMR is getting worse, but it's not terrible. And my CFI here is still in the good range, but I think this is a significant change, right? So just in case you're like me and math can be A struggle sometimes, simple math says 0.011. Goodness. So that is a significant change from the previous step. So one thing to note here is, unlike MTMM, where you control everything, compare everything to the first model, I'm actually comparing this one to the previous step, the metric invariance, because we're changing one set of things at a time. As we go from configural invariance to metric invariance, yeah, we're changing multiple parameters, but we're changing one type of parameter at a time. So I would compare those to each other. And then going from metric to scalar, I'm changing one parameter. I'm going from only loadings to loadings and intercepts. So now we are going to try to figure out what we can do to fix this problem. So let me add a line here. Let's see if we can come up with partial scalar invariance. Okay. And so just as a reminder, these are intercepts. Okay, so that indicates that somewhere in these intercepts, we have a difference in group means, essentially, for a particular item. And what you can do is what's called partial invariance. So partial invariance is where I go, okay, fine, the scale works pretty well for both groups except for this one question. And here's how that question works for group 1. Here's how that question works for group 2. And so that's important to know. I think this is particularly useful in a clinical setting, in the sense of that if you're going to use category score cutoffs, so like the Beck or the CESD, knowing that some groups take that scale differently was very important for you, because that implies that you should have different cutoffs for different groups. And so on the one hand, we'd want all of our scales to be perfectly equivalent across groups. We all know that's not probably possible, given that people are people. But on the other hand, it's good to know where things break down. Obviously, this should be repeated multiple times because one sample is not the answer to everything, but it is a good way to shed light on these scale issues and trying to figure out what scales are doing. So psychrometric questions can lead to a better understanding of the latent variable or the phenomenon you're trying to study. All that being said, let's see if we can figure out what questions it is. So sometimes it's just one question that's causing you a problem. If it's lots of questions, essentially you can't get to scalar partial invariance, and you just say they're equal up to this point, and then after that all bets are off. I don't know that there's a good rule for this. I usually think of it as about a third. If a third of your scale is very different across groups, then maybe it's time to rethink the scale, or just to note that, hey, the differences in overall group total scores might be due to the fact that people answer these questions this way and these other questions this other way. You can also work on equivalence that way, where you can test latent means based on their on scores separated for each group to then see what the overall totals are. And what that'll do is really awesome, because it lets you essentially treat each group separately in their weighted scores instead of just creating total scores or average scores from the raw data. And that'll let me know that, like, if I control for the fact that these questions are different, now we no longer see overall group differences. So it might be something about the way you're using the scale instead of inherent group differences, much like the issues with IQ testing. Okay, blah, blah, blah. Let's talk about how do I do partial fit. All right, so partial invariance. So we're actually going to copy all of this because you want to do partial invariance on the step that it broke down. So this is where we broke down. So I'm going to do partial scalar fit. Because we might do partial invariance twice. Hopefully not. There we go. So we've got partial invariance here, and I have to first figure out where the problem is. And so to do that, what you're going to do is use modification indices. So we're going to get the partial modification indices. So I'm going to do mod indices. And we're going to do that on the step we're working on, so scalar.fit. And if you just run that, it tells you that, it gives you a little warning saying this isn't perfect for equality constraints. And I said, great, I'm just using it to find what to test. And so you want to save them, because if you don't save them, it's a big old mess of all these things to look at and you will be miserable. So we're going to save them and subset them out. And so this is a list when I save it. So watch this. If I do ls, so tell me what's in this partial mod thing. Remember, ls just give me a list of all the options. We've got EPC group and all these other different things. But what we really want is OP here. So what is that? So I'm a partial mod. Give me, what is the OP column? OP is the type of operation that's going on. So I'm going to give you some little rules here of what to look for. So this applies to any type of multi-group model, and then we'll use the specific ones for this model. So if you are looking, if your model breaks down at metric, so actually the step above this, you are looking for loadings. So loadings are this type of operation equals tilde. Okay, so that indicates a loading. Now this can also be found on page 27, I believe, of the Lavaan book, where he talks about what all these different code pieces mean, but this is just kind of a reminder right here where we're actually using them. Okay. If your model breaks down at scalar, we're looking for intercepts, so that's a tilde1, so that is the code for intercept. Okay. If we were to break down at the next step, which we haven't gotten to yet, which is variances, sorry, it's called strict, but those are variances. So we're going to use double tildes. Okay, so this is loadings. These are intercepts. And then these are variances. And so that's what I'm looking for. So what I'm going to do is I'm going to subset out the partial modification indices and only get the intercepts. Okay. So let's go partial mod. And I'm going to say I want where partial mod is equal to, oops, gotta tell the right column here. The OP column is equal to intercepts, so tilde1. So look in that particular, this is actually a data frame, not a list. So look in that particular, look in all the rows and give me all of the columns back. So we want to look for the highest intercept. So let's get that intercepts one. And so if I just type intercepts down here, it's going to give me all the modification indices that are in order, actually, for each group of just intercepts. So that's the cool thing. That's what we were able to subset out. Okay. Now, one thing that you could do now is actually sort these bad boys. So I could do intercepts, and I want to sort by intercepts, okay, which is the order function. So intercepts, but we have to have the specific column we want to sort on, and I want to sort on MI. MI stands for modification indices, so I want to sort the modification indices. And I want to do that in a decreasing order. Sorry, decreasing equals true. Okay. So what does this line do? So what it does is it takes the intercept data frame that we have made, and it says order this data frame by the MI column. And so I want to order by rows and get all columns back. And what that does for me is it makes it a little bit faster to see which one's the biggest. So that just puts it in order. But you want to subset out here based on the OP column, the operation column. So only look at the ones you need. And then you want to sort by the MI column. And that will just give you the biggest one first. And so it looks to me, looking at this, output, that the one with the highest modification indice is going to be RS4. So that implies that there's something about RS4 for group 1 that is just cranky pants. Okay? And so there will be a change in modification indice if I do something different with that intercept. And so it'll actually appear twice because there's two groups. Often they'll appear together, but RS4 is our top candidate, so we're going to change that one first. Now on all of these, change one thing at a time. Okay, so you might have several steps, and that really gets at this question right here, but we're just going to change one thing at a time. So for our partial invariance at the scalar step, we have 0.912 as our CFI that we're trying to at least get close to. The lowest we could go is 0.01 lower than it. So we need 0.902. So we're actually really close, right? We just barely missed it. So I'm trying to get back to a CFI of 0.902 at my partial scalar. Okay. And so I've answered this next question. What question would I freely estimate? I'm going to estimate RS4's intercept is going to be allowed to be different across groups. So free estimation, remember, means that it is allowed to vary across groups because everything else has been constrained to be equal. Okay. So let's add that to our partial model. So what do I got to do differently than what I have now? Well, there's a group.equal function, and then there's also a group.partial function. And that means like, well, not everything can be perfect, so let these groups be partially invariant. And the cool thing is you can go straight from the modification indices. I'm going to highlight this little code here, and I can cut and paste that code directly in quotes here. Okay. And what that does is it allows the RS4's intercept to be free. And allows that to be different across groups. So the cool thing about pulling from the modification indices is you can cut and paste those directly into your group.partial. And then I just want to run everything. So if you're watching what we're doing as we go through this multi-group model, we are changing one piece at a time. And when we do the equal functions here, it's multiple parameters, but it's still just one thing at a time. And so when we get down to group partial invariance, it's still one thing at a time. So run that. So RS4 here, let's go look at RS4. What you'll notice is here under the intercepts, it now does not have a number next to it. So what happened? Well, this bottom group I think is whites. So their intercept's 4.24. I'm going to scroll up here and look at the black intercept, and it's 5.13. So blacks are endorsing more of this question, and whites are endorsing less of this question. So that implies that the black participants have a higher average for this question than white participants do. Okay, and that's kind of a big difference on a Likert-based scale. Did that give us enough change, though, to consider these models partially invariant? Let's run this fit measures line to find out. I said I needed a CFI of 902. I have a CFI of 907, so I am doing good. Okay. So I let one pathway be free, so I lost a degree of freedom. Okay, so RMC is 090, 058.907. And so I've already said I needed at least 902, and I'm looking pretty good. So I want to compare that to the metric invariance, though, not the scalar step. So we're trying to bring this step, which is a partial version of the scalar step, so you don't want to compare it to itself, back up close enough to metric to be, good enough for government work. And so that difference is 0.005. So I would say it is not different, which is what we want. And so now I have partial scalar invariance. Okay. Now warning here, a lot of people say that once you hit partial, you should stop. You should not do any of the other steps. That differs across theoretical backgrounds. And so I'm going to keep showing you what would happen with strict invariance, with the warning that some people say, well, you shouldn't do it. But here we've gotten to partial invariance. So we can say, really, okay, it's question 4's intercept. And so we could keep going as long as we keep allowing question 4 to do whatever it wants. So we're not going to reconstrict question 4 because we know that's bad. And so it's kind of like, oh, we had to divert a little, and this question, we know it has this issue, but what about variances? Okay. So some people argue that you shouldn't keep going after you stop. There's a lot of different ideas about multi-group testing. This is just one of them. Okay. All right, so what is strict invariance though? And these are going to be your error variances. And so this allows you to look at the variance for each question. So we're going to test if the residuals are the same for each item. So we've kind of worked our way from the latent variable out. So we went from loadings to average scores or intercepts to now the residuals. And we're going to see if they have approximately the same residuals across each group. What would it mean if they didn't have the same residuals? I get asked that a lot. And that implies that they have different distributions. So let's say that our white group on this one particular question had an average error variance of 1. Okay, and this is kind of the standard deviation, right? And so if our average score is a 4 and we vary around that question 1 point, that means most people are scoring between a 3 and a 5. Right? This is a basic interpretation of standard deviation. Is this the average distance away from the mean? If our other group on has the same average score, 4, but their error variance is 2, that means that they're endorsing a wider range of the scale. So they're picking from 2 to 6, where the other group is picking 3 to 5. So this almost tests the idea of kurtosis in a sense, but really what it's talking about is the spread of the distribution. So do they have the same spread, the same variance? And the way I really think about this when I'm talking about scale development is, do they endorse the same range, average range of items on the scale? So if I have a average score of 4, are we varying around that 4 approximately the same, or is there a wider range for one group than the other? All right, let's test that now. So let's get down into strict invariance. I don't know why it doesn't have a fancy name. It just doesn't. So I'm going to copy this code because I want to keep working my way down one step at a time. But now it's just going to be strict. It's really kind of partial strict invariance because we are going to leave that partial piece in there. And so I'm going to leave all this in here, this group.partial piece. And now I want to add residuals in here. Okay. And residuals will let me contest the error variances. Okay. Don't put in variances, that does something else. So I'm going to leave my group.partial alone and just test the residuals. So what you'll notice, if I did this right, let's make sure, oops, wrong window, is now all the variances down here are forced to be the same. And our RS4 is still doing whatever it wants. Okay, and it really shouldn't have changed because as we add constraints, the other items shouldn't really change across runs. So let's look at the fit indices, see how we did. So we've got 193 degrees of freedom. Our RNC is 0.092, RMR is 060, and we might be in trouble for this CFI. So if I take 907 and I subtract 893, I get 014. Darn it. So these are significantly different. So even though we've controlled for the invariance at the intercept step, I now have the problem that there's something about the residuals that aren't the same. Okay. And so for a partial residual step, okay, we did this just a second ago, so 907 minus 0.01, because we're going to compare this to the partial invariance step. Otherwise, you're never going to make it if we compared it back to 912 or something. And so that would be 0.897. Again, I am bad at math sometimes. Yeah. So 897 is what I'm trying to get to. And let's see if we can figure out what item's variances are different. So we want to do that same thing we did a minute ago with the modification indices. So let's figure out the issue here. All right, and so we want to do partial modification indices on the strict step. And I overwrote the ones before, and I don't know that it matters. Residuals, because we already passed that step. So residuals on our partial modification indices. So I want to do double tildes to get the residuals only. And let's look at how crazy that looks. Right, so I've got my tons and tons and tons of these things. Now, here's the issue. Let's look at these residuals for a second. What it's actually telling me here is that I should correlate the errors between RS12 and RS13. Okay, I don't want to do that. What I want to do is find ones where the residuals are the same on both sides. So it's telling me the residual correlated with itself is cranky, which means that maybe I should try releasing it for the two separate groups. And so I want to also add another piece, and this is particular to the residuals only, because in these, what you're going to look for is where it's like RS9 correlated with RS9 is the problem. In the intercepts, you want to find the highest one, and in the loadings, you want to find the highest one. So this is particular to residuals. So let's subset that out again, where what we're going to do now is where partial mod, the LHS, the left-hand side, is equal to the right-hand side, our RHS. Okay. So what that does, if I scroll down to the bottom here, you can see that LHS, left-hand side of the operation, RHS, the right-hand side of the operation. And so honestly, actually, we could just look through 1 through 14 here, because this is where they seem to all be at the top once they're sorted. But if you have 47 questions, that's going to be a lot of stuff, and you just want to be able to sort them. Let's just filter out and get only where they're equal to each other. Okay, so I want those two things to be equal. So let's decrease here. So now my residuals component is just those first 30 where they're equal to each other. And now I can sort them in order. So I'm just changing the name. So I still want to sort on my modification indice column. And that tells me that RS3 is the issue. So we're going to allow the residual for RS3 to be this different across groups. So let's highlight this little piece of code right here. Oh, actually, let's do one more thing first. So let's do partial strict. So I'm going to cut and paste my strict piece here. Stick that down there, and then change all this to be different. Partial strict. But now I'm going to allow something else to be partial, and this is where you can take and cut and paste the code from the top to the bottom. Boop. Right. And so now I'm letting, not only am I letting the intercept for RS4 be different, but I'm letting the residuals for RS3 be different. Okay. And it's one thing at a time. So the answer to this question would be RS3 residual. Eeks, just kidding. So let's try RS3. And let's run that, see what happens. So we'll see that the residual for RS3 for the white group is 1.79. For the black group is 3.31, so it's almost double. Okay. And so that implies that for RS3, okay, which is the average score is 4.1, it's the same for both groups. Black participants are endorsing from 1 to 7, like almost the whole range of the variable. Okay. whereas white participants with an average of 4 are only endorsing 2 points below and up, so 2 to 6. So you get a wider spread of scores for the black participants than white participants. And then let's look at the fit indices. So did we make it to our cutoff with just one question? Now, on this particular example, we'll have only one question. That's the problem for each of them, or one item. You can do multiple questions, and you will have to figure out what your cutoff is. So if you have 40 questions, 4 is not so bad. 20 of them would be clearly bad. And I actually already said that 0.897 was my cutoff, because I figured it out a minute ago. And so I'm comparing that, remember, to the last step that worked, the last no, essentially, out in this column. Now, this column isn't required in a write-up. I just have it so you can see what I'm doing. And it's not significantly different from this partial scalar invariance step. And so that really gets me to this last question. Interpret my findings. Are the groups invariant? Mostly. Okay. The loadings are definitely invariant. The intercepts are invariant except this RS4 question, and the error variances are invariant except this RS3. Okay, so did I see a breakdown between groups? Yes. What does that imply? There are different average scores for RS4, whereas one group has a higher average score than the other. And I would go back and look at the original question on the scale and talk about maybe what that means theoretically, like why are we getting different averages for each person. On the error variances, well, it kind of just ended with that, but they're endorsing a different range of the variable. So for this particular question, even though we have the same average score, white participants are only using some of the scale, whereas black participants look like they're using the entire scale. So why are we getting different range of scores for these different participants? So that is a set of steps for a multigroup model, including partial invariance and how partial invariance works, using the general Brown terminology. In the next video, I will do another one of these and also talk about latent means and how to calculate weighted average scores and test if those are different overall.